Okay, so for section 4.5, we are looking at using Newton's method to solve equations. That's our EQ. Now there's a couple other components to it that we'll look at. One of them being the idea of a linearization. Now, this is one of those areas in math where a familiar concept sort of gets a new name. So on the screen here it says graph y equals x squared. You can take a moment to do that. Zoom in at x equals 1. What do you notice? Now, we did this the first day of school, and what you should notice is that that curve becomes linear. We call that local linearity. Any function that is continuous and then differentiable, nice and smooth, when you zoom in, you should get what appears to be linear. So the part that appears new is we have this formula for a tangent line that we call a linearization, like a linearization being the idea of making something linear, making the function linear in its neighborhood. And then in essence, typically using that to estimate, function values close to the point of tangency. So if you look at the bottom here, it talks about using point-slope form of an equation. So y minus y1 equals m times x minus x1, solve for y, and that's the format that I have been using a lot to write tangent lines. Slope times x minus the x value plus the y value, but notice they have the y value first here. Now, the substitution that's being made is just thinking of it in terms of function values, inputs and outputs, instead of x's and y's. So the a in this case is the x value that you have. The slope would of course be that value plugged into the derivative, that's f prime of a, and then the y value would be the function when a is plugged into it. So thus the f of a plus f prime of a times x minus a. So the reality is any problem that's asking for a linearization, it's just asking for a tangent line. So we often use L of x to represent the function form of that linearization, and there's the formula again, and it's basically used to estimate function values near the point of tangency. So at the point of tangency, the tangent line should match the curve, and close to it, it should be relatively close. Now a couple problems for finding a linearization. The first one there, find the linearization of square root of 5 plus 4x.
Could you please report to 508? Susan Robertson to 508.
At x equals 1. And so we need three things. So instead of xy slope, which I have been usually stressing, if you're making a tangent line, you need x, you need y, and you need slope. They're calling the x the a value. They're calling the y f of a. And they're calling the m the f prime of a. So here the a value is then 1. F of a I can plug into the function. I can do that in my head. 4 times 1 is 4, plus 5 is 9, and the square root of 9 is 3. So I'm looking at that first function there. So f of a is 3. And for f prime of a, well, I need a derivative. So I'm going to take the derivative of square root of 5 plus 4x. So I'm going to picture that as to the 1/2 power. Bring down the power. Reduce it by 1. So it would be negative 1/2. Multiply by the derivative of what's inside, so multiply by 4. I'll get it back into a pluggable friendly form, and that would be 2 times, whoops, backtrack a second, that is a negative 1/2 power. So I'm going to go 2 over the square root of 5 plus 4x. So f prime of 1 would be plug a 1 in to this guy right here. 4 times 1 is 4 plus 5 is 9. The square root of 9 is 3, so I've got 2/3 as my f prime of a. Therefore, if I'm using the linearization form of the tangent line, it'd be L of x equals f of a plus f prime of a times x minus a. and there's my tangent line. So I can use that to estimate values very close to x equals 1. We had a similar problem on a recent test where you were finding a tangent line and then estimating and comparing. So we'll do a little more with the linearization and comparisons in class, and then take a look at Newton's method. So Newton's method, what a really cool idea. The idea being used to solve equations that would not have been able to be solved algebraically before. And you're not actually getting an exact answer. You're getting an answer to whatever degree of accuracy you can. Now, so the first question there says, use Newton's method to solve x cubed plus 3x plus 1 equals 0. Now, we, a while back, proved that did have an answer by using the intermediate value theorem. That is a continuous function. You can plug in an x and get a negative answer. You can plug in an x and get a positive answer, but what's the solution? Okay. Now we can use technology to get that. There actually is a cubic formula you can use that you probably never learned in your algebraic career, but we can use Newton's method to do it. Now, Newton's method is what we would call a reiterative algorithm. You just keep reproducing the algorithm until your answer gets closer and closer to what you want it to be. So the first thing you do is you just make a guess as to what you think would be reasonably close to the answer. We'll call that x sub 0. So I'm going to say, well, I don't know, if I plug 0 in for x, I get 1. So if 0 cubed plus 3 times 0 is 0 plus 1 is 1. 1 is relatively close to 0, close enough here. So I'm going to start with just a bad guess of x equals 0. Now, if you look at the formula here, it says x sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n. And so you're taking your guess and you're generating a better guess. So we'll call that better guess x sub 1. So that's the n plus 1 there. That's the subscript. Remember, subscripts are labels, nothing to calculate. And it says take your guess minus your original guess plugged into the function divided by your original guess plugged into the derivative. So I need a derivative. So somewhere along the way, I'm going to write this down at the bottom. I'm going to take the derivative of the function that was right here, x cubed plus 3x plus 1. So the derivative would be 3x squared plus 3. So it'd be 0 minus f of 0 is 1. F prime of 0 would be 3. So negative 1/3 would be considered a better guess at the answer. What's a better one? Go to x sub 2. And it's saying take your last answer minus your last answer plugged into the function over your last answer plugged into the derivative. Oops, forgot my prime. There we go. And so that would be negative 1/3 minus f of negative 1/3. Whew, okay, so I'm going to do a little mental math. You may have to check me, but I've got negative 1/3 cubed. That would be negative 1/27. But then it'll be plus negative 1 plus 1, that's 0. So that actually works out kind of convenient to start. It's negative 1/27. Check it if you're not sure. Then plug negative 1/3 into the derivative. So negative 1/3 squared is 1/9. 3 times 1/9 is 1/3. 1/3 plus 3 is 3 1/3. That is 10/3. So I'm going to simplify that expression. I'll flip and multiply the top, so I'd have negative 1/90th. And that expression, wait, hold on. Reciprocate 1/9, yep, negative 1/90th. So it's going to be minus a negative, so it'll be plus 1/90th. So this negative 1/3, that would be negative 30/90th, plus 1/90th, that's negative 29/90th. So you can see how tedious this would be. But what you do is you keep proceeding with that until your answer that you're getting does not appear to change very much. So what we can do is we can do it on the calculator. And so Turn on the calculator. And have a few steps over here for you. It says enter the function in y1. So it's pretty nifty how this works. Go to y1, clear that out. The function is x to the third plus 3x plus 1. Derivative in y2, 3x squared plus 3. Get out to a blank screen. Make a guess. I guess 0, and you store it for x. And then what you do, this is pretty cool, take x minus vars y vars function y1 divided by vars y vars function y2. You don't need to use function notation on the y1 and y2 because if you don't, it implies whatever you have as x is being plugged in. So we made 0 to be x. I'll press enter, and look what I get. Voila, negative 1/3, which was our first calculation. I press enter, and remember the calculator will redo the last command. I just realized I made a mistake because watch, it's going to keep saying the same thing. So let me fix that. It is 0 store x. I forgot to restore it. So x minus vars y vars function y1 divided by vars y vars function y2. I want to restore that in x. Hit enter. Now nothing changes because it calculated it, but now that's the new x number. So when I hit enter, it'll reevaluate, restore in x. That right there is negative 29/90, which we got on our second round. Press enter again, and look, we're already accurate to 3 decimal places. So that's an AP answer right there, negative 3.22. Press it again, and you'll notice it matches out to the 1, 2, 3, 4, 5, 6, 7, 8th decimal place, 9th if you round. One more time through. So a pretty amazing process. Like we were guessing a relatively close answer, and within a few steps of Newton's method, we came to a very reasonable answer, out to many decimal places. Okay, there's a few other components of Newton's method, but as we work through the problems in class, we will go over that and show you a little bit about why Newton's method works. It's really just a linearization, which is kind of what it says down here. From where does Newton's method come? It's using the idea of a tangent line, and we'll look at that in class.